Kohlrausch law. There are three applications. Calculation of molar conductance at infinite dilution. Molar conductance. The molar conductance can be represented like this at infinite dilution. This can also be represented by some authors as mu naught. Okay. What is this? Molar conductance at infinite dilution. And secondly, especially molar conductance at infinite dilution of a weak electrolyte. Because the strong electrolyte readily ionizes, but weak electrolyte slowly and incompletely ionizes. So it will be very difficult to find out the molar conductance of such weak electrolyte, but using Kohlrausch law we can find out. Secondly, we can calculate the degree of dissociation. Degree of dissociation of weak electrolyte. Third one, we can calculate the solubility of sparingly soluble salt. So it's known as a KSP, solubility product. It is represented as solubility product. So what is this? Molar conductivity or molar conductance of weak electrolyte at infinite dilution. Second, degree of dissociation of weak electrolyte. Third, solubility product. 1, 2, 3. Let us see one by one. Let us consider the first one. Molar conductivity at infinite dilution of weak electrolyte. It is impossible to determine the molar conductance at infinite dilution. Why? Because experimentally it is ruled out, because it weakly dissociates. So using the equation, for example, let us consider acetic acid. I am interested to find out the equivalent conductance or molar conductance, not equivalent, molar conductance of acetic acid. So this is a weak electrolyte. We cannot get directly ionic conductance of molar ionic conductance of CH3, COO and H plus like this directly. Instead, we can have the rule. Instead of acetic acid, we can take acetate, that is a weak acid with its strong base. Okay, a weak acid with its strong base. So strong base is Na, is it not? So this is the salt. So this is the salt of weak acid with its strong base. strong base. And from this we can have, you got the Na plus, is it not? So let us find out for this salt the molar conductance at infinite dilution of CH3COONa. Usually you have to write down the cation first. So Na plus ionic conductance of CH3COO minus. Okay. Then we had to consider the molar conductance of NaCl, so that it has the common cation here. So this is also strong electrolyte, so we can dissociate this as Na plus and Cl minus, right? Okay. So this is equation 1, this is equation 2, this is equation 3. Are you will follow? And let me consider HCl also. Okay. So for HCl, molar conductance at infinite dilution for HCl can be molar ionic conductance at infinite dilution of H plus plus, and this one MCl minus. Okay. So this is equation 4. So my objective is to get the CH3COO minus and H plus only. This is our target. So by combining this equation we can get it. How? For example, you have got the CH3COO Na, so we have split this as ion. Let me take this one, 2, equation 2. And we are not interested in Na, so you can subtract 3. But at the same time we have to get the H plus, so we can add this, so we can get it. Okay, so this is the easy way you can get it. So take equation 2, subtract 3 from that and add 4. Got it? So what is equation 2? This one. Let me take the RHS only. So what is this RHS? That is, consider RHS only. Okay. So we have taken Na plus and CH3COO. So ionic conductance of Na plus ionic conductance at infinite dilution of, what is that? CH3COO minus. Got it? Minus. Third should be subtracted. That is ionic conductance at infinite dilution of sodium. Since it is minus, we have to put again molar conductance at infinite dilution of Cl minus. Are you able to follow? Then add fourth one. Add 4. So H plus Cl minus. Okay. Now what you can do? Now we are adding this. So Na plus and minus cancelled. Then minus Cl plus Cl cancel. Okay. Now we can add this. CH3 COO minus, okay, and then plus ionic conductance at infinite dilution, molar conductance at infinite dilution for the ion H plus, and this is nothing but the molar conductance at infinite dilution of CH3COO. So indirectly we can find out. Got this? Right? Similarly we can try with the base also. Okay, weak base. Now let me proceed with the calculation of degree of dissociation of weak electrolytes. So this is the second point. Okay, so how to find out the degree of dissociation based on Kohlrausch law, right? Second point, we had to find out alpha, which is called a degree of dissociation. So this is obtained from degree of dissociation alpha, that is molar conductivity at infinite dilution. Molar conductivity at certain concentration divided by molar conductivity at infinite dilution. So what is alpha? Degree of dissociation of weak acid, okay, or weak electrolyte. And what is lambda m? Molar conductivity at certain concentration, and this is molar conductivity at infinite dilution. Okay. Now, according to Oswald's dilution law, it's called ODL, Oswald's dilution law. ODL states that dissociation constant of an acid is equal to alpha squared C divided by 1 minus alpha. So we can suitably substitute here. Therefore, Ka dissociation constant is equal to lambda, and we, instead of alpha, we can put lambda m divided by lambda naught m whole square. Is it not? So we can put square into C divided by 1 minus alpha, means 1 minus lambda m divided by lambda at infinite dilution. Are you able to follow this? Now let us consider Ka is equal to, so lambda squared m divided by lambda naught m squared into C, take LCM, lambda naught m minus lambda m divided by lambda naught m. Okay, we can reciprocate this. So lambda squared m divided by lambda naught, this is naught m, that is at infinite dilution, into C divided by lambda naught m minus lambda m into lambda naught m. So we can strike out the square. Got it? And finally we are able to get Ka is equal to, that is lambda squared m into C whole divided by lambda naught m into lambda naught m minus lambda m. So by determining the lambda naught m and the lambda, we can find out the dissociation constant. Got it? Next one, calculation of solubility of product of sparingly soluble salts. It's called simply KSP. solubility product of, what is KSP? Solubility product of sparingly soluble salt. What do you mean by sparingly soluble salt? It is not completely soluble. Like silver chloride, barium sulfate, etc. Let me consider AgCl, PbSO4, lead sulfate, barium sulfate. These are all causing some precipitates. So it won't be completely soluble. So they are sparingly soluble, okay, partly soluble. So in that case, AgCl, let me consider being a solid. Now it undergoes an ionization like this, Ag plus Cl minus. Then AgCl gives Ag plus and Cl minus. So what is the KSP for this? That is equal to Ag plus concentration into Cl minus concentration divided by AgCl solid concentration. This has taken as unity, that is 1. Okay, so you can remove this. Therefore KSP is equal to Ag plus into Cl minus. Okay, in fact the concentration of Ag plus will be simply C or S. So you can call it C mole per liter. So this is C mole per liter. And what about chloride? That is also C mole per liter. So KSP is equal to, you can simply put C into C, that is C squared. Okay, so this is called KSP. And we already know lambda naught, molar conductance at infinite dilution, is equal to kappa into, kappa is conductivity, okay, 10 power minus 3 divided by the concentration term. Usually this concentration term in mole per liter, and that is why we have put 10 power minus 3 as liter. So from this we can calculate C. So you can put kappa into 10 power minus 3 divided by, and these are all the experimental values. So based on this you can find out the concentration of a given sparingly soluble salt. And if you want to represent the KSP, we already know KSP is equal to C squared. So you can substitute here. Therefore KSP is equal to kappa into 10 power minus 3 divided by lambda naught whole square. Okay. So likewise we have 3 important applications of Kohlrausch law. One is we can calculate the what? Molar conductivity at infinite dilution of a weak electrolyte. Second, dissociation constant or degree of dissociation. Dissociation constant means Ka for weak acid, Kb for weak base. Alpha is degree of dissociation. So we can find together these. Then similarly we can find out the KSP values also of sparingly soluble salt. Okay. So these 3 are very important applications of Kohlrausch law. Okay.